this chapter has less math and is about acids and bases, which is good. I think you will like it. But there is definitely some math, but towards the second half of the chapter. So the first thing that we're going to do today is we're going to compare the different acid-base theories that happened over time. So what scientists first thought was an acid and a base, and then later what they figured out was an acid and a base is different. So we have to kind of go through their evolution with them. So there's 3 theories, and that's what I handed out on your little cheat sheet. And that cheat sheet is definitely going to need some stuff added to it. But the 3 theories are in order of oldest to newest. So Arrhenius was the first theory, then Bronsted-Lowry, and then Lewis. So we're going to talk about each one, but you definitely need to memorize each one because they are a little bit different. And probably when we're talking about it, you're going to be like, I don't get it. I'm just going to be honest. And then as we practice, it's going to make a little bit more sense. Probably with everything that we do in this class. Okay, so let's talk about overall properties of acids. Acids taste sour. Not that we know, because we're not tasting them, but they are sour. Think about citrus fruits. They have acid in them, and they are sour. They can conduct electricity. Now, this isn't like I'm going to stick electricity in a lemon, but in solution, they can conduct electricity. When they react with metals, they form a hydrogen gas. We already know a little bit about acids back when we were naming them, and we know that they have hydrogen usually in the beginning of them. But remember that? But they do react with metals to make hydrogen gas. And then we know that we've used pH paper before, litmus paper, and so they change the color. That's not really that important. But the reason that when we learn about acids, we learn about bases is because they react with bases, and then the overall reaction or the products of that reaction is to make a water and a salt. Please keep in mind when I say a salt, I don't just mean sodium chloride, I mean a metal and a non-metal. So I'm not really picky about the color changed one, but sour, conduct electricity, react with metals to make hydrogen gas, and then react with a base to form a water and a salt. Now, when we get to bases, you're going to understand why it says metallic hydroxide, but I understand if that seems weird at this point. That's okay. We will get there. For me, just write the top one. Don't worry about carbonates and bicarbonates just yet. They have a pH of less than 7, which you already know. pH of less than 7. And we will get to pH later. For now, we're just going to focus on the theories. But don't worry about carbonates and bicarbonates for now. So, in a chemical equation, how do we know that a compound is an acid? Well, we already worked through naming of acids. We know that it usually starts with hydrogen. That doesn't necessarily mean just one. We've had examples where, like in sulfuric acid, that second one, it says H2SO4. Okay, but usually start with hydrogen, but not water. Water is not an acid. Okay, and we'll flip through this. We already know all about this. I'm going to talk about bases, and then we'll come back to some of this. Again, I'm going to talk about bases, and then I'm going to come back to some of this. Blah, 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 blah. Okay. Let's talk about a base, and then we'll go back to that reaction. So a base, and in parentheses it says metallic hydroxide. Okay, let's break that down. So we mean a metal and a hydroxide. What is hydroxide again? On your bookmark?
OH.
OH, good. OH minus. So we're talking about potassium hydroxide, sodium hydroxide, lithium hydroxide, calcium hydroxide, a metal, and a hydroxide. That's what our base is. Okay? So they're easy to pick out. So the properties of those bases are they react with acids, again, to make a water and a salt. They taste bitter, which we are not going to test. They are slippery. We are not going to rub them all over our faces.
If we can't taste it, why do we say it tastes
I
good?
don't know. That's a great question. Not really sure why. And I never understand why that's listed first. Like, I can understand listing it, but why list it first? Because then that just makes people want to go, are you sure? Can be strong or weak electrolytes in solution. That really just means when they're mixed with water that those ions are going to separate. And they may be able to conduct electricity. And then again, I'm not worried about indicators. I think you've all used pH paper before. So they're all hydroxides. It's real easy to pick them out. Lots of them are cleaners. Again, there's my paper. And so let's go back to that reaction. So on both of them it says that they neutralize each other and make a water and a salt. So let's take a look at that reaction. And I want you to write out kind of the skeleton formula of that reaction. Oh my goodness. There you go. So instead of writing HCl plus NaOH, you can, but sometimes an easy way to kind of generalize an acid is to do H and then the big letter A. And that just means any acid. So big H, big A. And sometimes the base, instead of a metal, it'll put a B, a big B for base, and then OH. And then in the products, your products would be A and B, AB, and then water. So they neutralize each other. When they are mixed together, they each split apart into their ions, and then the metal and the non-metal form the salt, and then there's water. And we're going to do some labs about this.
So the B equals the metal?
The B is the metal.
And
The A is the negative ion that's in the acid. Good question. Not to say it's always going to look like that, but I think if you read through the text in this section, it does use that kind of generalization. All right, so let's get to these bases. These theories. Oh my goodness. Okay. I'm not really picky about their little background of their life. Here is the Arrhenius definition. And these go from narrow to broad. So not only is this the first definition, but it is the narrowest definition. That means it includes the least amount of compounds that actually are defined as acids and bases. So he said that acids produce hydrogen ions in solution. So they have to have hydrogen ions to be considered an acid. And he said bases produce hydroxide ions in water. So he limited acids and bases to when they were in aqueous solution. And he said that there was only one kind of base, which are hydroxides. So if it doesn't end in OH, can't be a base. Again, this is the first theory and the most narrow, or includes the smallest group of acids and bases. You have this on your little cheat sheet. You may want to put the word produce in front of H plus in H2O. Just to remember that if you mix that acid with water, it's going to produce, or that the hydrogen ions are going to break apart. Okay, I'm going to skip through that. Okay, we've already talked about this a teeny bit when we were naming our acids. We know that not all acids just have one hydrogen in the beginning. We know to balance out, because of the polyatomic ions that they are, or maybe a -2 charge or a -3 charge, that sometimes there's more than one hydrogen in front. And so Arrhenius didn't say just one hydrogen ion is produced. He just said an acid produces hydrogen ions. So for phosphoric acid, it would make 3 hydrogen ions because it has 3 hydrogen ions. Or sulfuric would be 2. And there's a name for this. If it has 1 hydrogen in the front, it is called monoprotic. If it has 2, it's called diprotic, and 3 is triprotic. And that's it. It doesn't go higher than 3 because the charges of our polyatomic ions don't go higher than -3. So acids that have more than 1 hydrogen are called polyprotic. More than 1 hydrogen. There's 2, it's called diprotic. 3 is called triprotic. Okay, I'm going to jump past this because I think it's pretty obvious. So the next theory is Bronsted-Lowry. Those were 2 scientists working together, Bronsted and Lowry. And it is a broader definition than Arrhenius. So it includes more compounds as acids and more compounds as bases. And the Bronsted-Lowry theory says that an acid is anything that donates a hydrogen ion. That donates a hydrogen ion. So not just is the hydrogen ion in the aqueous solution, but it gets donated. It goes to something else. And what does it go to? A base. The base is the hydrogen ion acceptor. So in Bronsted-Lowry's theory, one compound, the acid, is donating or giving away a hydrogen, and then the base in that equation is accepting. And Bronsted and Lowry came up with this idea that acids and bases always come in pairs. If one is donating, then the other is accepting. And they are called conjugates. The pairs are called conjugates. So the example there is hydrochloric acid in water. Notice we're not a hydroxide here for that base. Water is acting as a base in this example. And so the hydrochloric acid donates the hydrogen and the water accepts. So the water would be the base in this scenario. So, of these acids and bases that are in pairs, they have a name. They're called conjugates. So a conjugate base is the remainder of the original acid. So after the acid has donated its hydrogen, what's left is called the conjugate base. Okay, so in that previous example, HCl was the acid, and then the Cl- was the conjugate base, what's left after the hydrogen has left. And then the conjugate acid is the particle formed when the base gains the hydrogen ion. So the water was the base in that previous example, and the hydronium, which was H3O+, is considered the conjugate acid because it has received the hydrogen ion.